Did you know that Death Valley, the lowest, hottest, and driest point in North America, used to be submerged in a shallow tropical sea? In this video, we are going to walk through the incredible geologic history of Death Valley. But I'm not here alone. I'm here with the amazing groove geologist and seismocam. And later, Kate and Cam are going to help us understand one of the coolest parts of Death Valley National Park. And spoiler alert, it may or may not have to do with some craters. So stick around for that. But first, let's go through how this valley came to be. To start, we have to travel back over 1.7 billion years to the Precambrian. The oldest rocks here are metamorphic schists and gneisses, which we call Precambrian basement rocks. They can be found in the mountains surrounding the valley, specifically the Panamint Mountains to the west and the Black Mountains to the east, which I'm standing in right now. These rocks became metamorphosed or heavily altered by heat and pressure during tectonic collisions along this western margin of North America, at the time Laurentia, possibly associated with the formation of one of the very first supercontinents, Rodinia. When Rodinia broke up, the west coast of Laurentia, what is now North America, rifted away from neighboring continents and became a passive continental margin, meaning that there was no active plate boundary at this coast or margin like there is today. The eastern margin of North America is a modern example of a tectonically passive margin, essentially where it just goes from continental crust to oceanic crust, but there's no boundary there. They're on the same plate. Now, obviously, the western margin of North America is extremely tectonically active, and it is at a boundary. So how do we know that this currently very active margin was once passive? Well, sandstone, siltstone, limestone, and dolostone here from around 1 billion to around 600 million years ago record this shift from tectonically active to passive margin because these sediments formed in warm, shallow marine systems undisturbed by tectonic forces. These rocks also record the proposed Snowball Earth events or near global glaciations that occurred around 700 million years ago, and the rise of multicellular animals that followed. Yep, that's right. There have been Ediacaran fossils found here that help us piece together what the earliest animal ecosystems on Earth might have looked like. And if you want to check out some of these figures that I've just shown in more detail, I highly recommend checking out this paper by MacDonald et al. On the rocks in Death Valley that provide this record of these Neoproterozoic events, including Snowball Earth, early animal evolution, and more. So it'll be linked below. And because this margin remained tectonically passive for almost the entire Paleozoic era, a series of shallow tropical seas covered this region throughout this time. So the fossils don't end there. Paleozoic rocks here preserve many incredible transitions of life throughout this era. From trilobite fossils during the Cambrian explosion over 500 million years ago, to 400 million year old early jawless fish, and even 350 million year old coral reefs. So how did this warm, shallow sea teeming with life transform into the arid, seemingly inhospitable desert that's here today? This brings us toward the end of the Paleozoic era, around 300 to 250 million years ago, when the next supercontinent, Pangaea, began forming. While the western margin of Laurentia, or what is now North America, wasn't directly involved with the continent-continent collisions that formed Pangaea, it did see tectonic activity again starting around 200 million years ago. Wait, back up a second. I'm glad I fact-checked myself because what I just said isn't the full truth. This margin was in fact tectonically active earlier in the Paleozoic era. It's just that the tectonic activity it saw at that time is a tad different than what it experienced post 200-ish million years ago and up to today. Let me show you what I mean with some diagrams. So this is a cross-section figure of the Laurentian margin when it was passive during the middle of the Devonian period around 390 million years ago. The thin white line is the oceanic crust, and the thicker white sections are continental crust. And you can see that left of the passive margin of Laurentia, the part that moves from continental crust to oceanic crust with no boundary, the oceanic crust portion of that plate is subducting underneath an island arc. It would have looked kind of like this. And as we move through the Paleozoic era, you'll see that this is a common theme, where island arcs come in and eventually collide with Laurentia over and over again. So moving to around 350 million years ago, we see the margin becomes active again because that island arc kept moving toward it, kept subducting that oceanic crust, finally ate it all up and collided with the continental crustal part of Laurentia. Then around 320 million years ago, we see the margin becomes passive once again with that antler island arc essentially just sutured onto it. And then it stays passive until another island arc collides, which we call the Sonoma orogeny. But notice up to this point, the subduction has been going underneath the island arcs, not underneath the Laurentia continent. Around 200 million years ago, this changes. An oceanic crust begins to subduct underneath Laurentia. This is what I mean with the tectonic activity that the margin experienced during the Paleozoic being different than today. It's the direction of subduction is what I meant to clarify with that. And eventually, we see the Nevadan orogeny, the Sevier orogeny, and the Laramide orogeny, all huge mountain building events that formed the mountains and topography that we know and love today across Western North America. And these orogenic events began when the Farallon Oceanic plate began subducting underneath the North American continental plate. And that caused major volcanism along this margin and thickened the crust. Over millions of years, as the Farallon plate moved eastward underneath the North American plate, it hydrated the mantle wedge above it, weakening and stretching the crust further inland. And then around 20 million years ago, this crustal stretching began to form what we call basin and range topography across pretty much all of Western North America, because these stretching forces led to what we call fault-blocked basins, where large blocks of crust have dropped down between faults, forming this repeating basin and mountain range pattern. And Death Valley is one of those basins. Like I mentioned earlier, the Panamint Mountains and the Black Mountains surround Death Valley. The fault between the Black Mountains and Death Valley, the Furnace Creek Fault, is actually still active, contributing to the dramatic relief between the peaks of these mountains and the lowest points in the valley. And even though Badwater Basin in Death Valley is the lowest point in North America, currently at around 282 feet below sea level, the valley floor continues to drop due to extension along these faults. But does this mean that these active faults still cause earthquakes here? Well, let's ask an earthquake scientist.
The simple answer is yes. Most of the faults here in the region do still produce earthquakes. Major earthquakes in the order of about 6.5 to 7.0 or greater happen about once every few thousand years here. But minor earthquakes, on the other hand, happen pretty frequently, every couple of weeks, but it's probably going to be a while until this region actually sees a major earthquake directly in the valley.
The tectonic activity along the western margin of North America today is driven by the subduction of both the remaining segments of the Farallon plate as well as the Pacific plate. And because the Pacific plate is moving a bit more sideways along rather than straight into this margin, this has created what we call transform faults or strike slip faults, like the San Andreas Fault, which remain active due to this plate motion. But hold up, before we get to modern day, let's get back to our story, the geologic history of this region. We left off around 20 million years ago when basin and range topography began to form in Western North America. Now jumping forward to the Pleistocene Ice Age, which started around 3 million years ago. Death Valley's topography was similar to today, but it still wasn't an arid desert quite yet. Believe it or not, it was actually home to a massive lake system, including Lake Manly, which stretched for over 100 miles or 160 kilometers in length. But as climate has warmed, these lakes have dried up, leaving behind the salt flats and playa lakes that we see now. These salts formed here because as the lake water evaporated, it left behind the minerals that were dissolved in the water. But it isn't just salts that have been left behind here. There are also sand dunes, moving rocks, and even craters in Death Valley National Park. So let's check in with Kate and Cam to see if they can't tell us about some of these features. Let's start with the craters.
We are standing here at Ubehebe Crater, and it is a little bit breezy, as you can tell. But this crater formed roughly 2,100 years ago when shallow magma interacted with groundwater, creating a violent steam explosion. This explosion could have even been comparable in size to the eruption of Mount St. Helens.
As you can see behind me, there is a distinct difference between those orangey sedimentary rocks and then some black layers of rocks. I want you to guess which ones were from the eruption. So we started out with all this older sedimentary strata. Those are sandstones and siltstones that otherwise would have been buried. So even though this huge explosion just like uplifted everything and just upended it, now we can see those where we wouldn't have been able to before. And then on top you had all of these pieces and just shreds of basalt. Even down at the bottom of the crater, you can find vesicular basalt, scoria, even some really cracked pieces of quartzite that were just disrupted due to this huge explosion. I came here 6 years ago for field camp. Here's my little notes and everything. And it was also windy as hell, and I wrote that in my notes. I thought maybe I'd get lucky. Dude, that's just how life works for me. So you can actually see right here, I actually had drawn a fault. Wait a minute, a fault? Cam, what happened? What happened there?
So the funny thing is, the whole reason this volcano exists is because of that fault. And it's actually found on the very western edge of the crater. You can see the difference in the color of the strata vertically. But essentially, all this extension that's been going on in this portion of the valley allowed magma to intrude into the crust, eventually interacting with the shallow groundwater, creating a series of explosions, because this is not only the main crater that is here at Ubehebe Craters, hence the name Ubehebe Craters. There's several more craters off in this direction over here, but they are not nearly as big and impressive as this one. This is about as good as you can get.
And take a look at this. It's a pretty good drawing for an undergrad, if you ask me. We can't remember if that's blood or if it was pieces from the, like, you can see down into the crater. There's actually some like of that like orangey stuff. When I came here, that was wet because it was just raining the previous, like the morning of, so that was all wet. So either I dropped this in a mud puddle of orange or I had cut myself on the very sharp rocks here. Let's go back in the car. My hands are numb.
Okay. Now to Racetrack Playa to see how these rocks move around this flat, dry landscape. I'm at Racetrack Playa asking the real questions. How did you get here? Okay, the mic wasn't working for Mr. Rock, so I'm just going to relay what he told me to you all. On the rare occasion when it rains here in Racetrack Playa, temporary lakes called playa lakes can form. And if there are rocks on the playa, sometimes they poke out over the lake because the water is super shallow. And during the winter, if it gets below freezing at night, these lakes can freeze over. And this traps the rocks in the ice. And then in the early hours of the morning, as the ice begins to melt, the wind starts to blow these ice sheets across the playa. And rocks that are stuck inside them scrape the surface of the playa. Remember, at that point, it's wet and mucky and clay-like, so it's easy for them to scrape the bottom. And this creates the tracks behind many of the rocks here. And even though the wind is super strong here right now, if you haven't noticed that from the rest of the video, this mechanism can apparently start to occur at wind speeds as low as 10 miles per hour. So it doesn't have to be very strong to cause this. And the craziest thing about this phenomenon is how long it took us to figure it out. These moving rocks remained mysterious for so long because these conditions are so rare. And not just rare to occur, but also, and especially, rare to witness. It actually wasn't until 2014 that these moving rocks were finally caught on camera. But what about these sand dunes? How'd these form? Well, these dunes, which are called the Mesquite Flat Sand Dunes, or at least the ones that we're at, get their sand from weathering and erosion of primarily granitic and sandstone rocks from nearby mountains, like those in the Panamint Range. Strong winds, typically northwest winds, pick up the sand from dry lake beds and alluvial fans adjacent to these mountains and carry it eastward. And because only certain grain sizes can get picked up and carried that far by wind, this sorts the grains so that the very fine material forms these dunes, making them super soft. In addition to all our fun solo adventures, we also got to attend a ranger talk at Badwater Basin while visiting Death Valley. The way that she explains the basin and range extension in this area was so brilliant, and she even had little visual aids. It was incredible.
A full bookcase, if you take a book out of it, what happens? The books fall over and they tilt, right? So that's exactly what's happening as the crust is being ripped apart. They will tilt over, and that creates the valleys in between the ranges here. I'll show that a couple more times. Just like that.
Honestly, I don't know if I'm more happy to just like be at a ranger talk and like see a geologist, like a park ranger just talking, or if I'm more excited to see people who aren't geologists be so invested.
I know, I love this. This is
Like this, it's
so
so
cool. Oh, yes. And she even goes on to talk about all the mountain ranges surrounding Death Valley, which contribute to this rain shadow effect and the whole reason behind how little water Death Valley actually sees. And for this demonstration, Kate and Cam volunteered to act as a couple mountain ranges. And each person / mountain range held a cup that she filled partially with water, representing the percentage of water received by each mountain range leading up to Death Valley, and then how there's pretty much 0% left for Death Valley itself. It was a really cool and fun demonstration that got people involved, which was super fun. But anyway, now to my favorite thing about Death Valley. Despite its currently extreme and seemingly inhospitable environment, this valley is actually full of life. Well, microbial life, that is. And these microbes might help us better understand what to look for when we search for life on other potentially similar worlds, like maybe Mars, for example. But if you want to hear more about that, make sure to check out next week's video. If you are interested in coming out to Death Valley and want to understand what you are looking at as you drive through, I highly recommend the Roadside Geology and Geology Underfoot books for this region. We were constantly looking through these books for help. They're just so useful with such great figures that match exactly what you see in person. Anyway, these will be linked below as well. Currently holding my hat on because it's so windy. Oh my god. Here from around 1 billion to 6, wow. From trilobite fossils. Cam, say hi.
Howdy.
Wait. Okay, you are Californian. First time here.
First time
Wait,
in Death Valley.
What are your thoughts? You have to hold this.
It is a lot to take in. This is honestly probably the biggest valley I've ever stood in, which is saying a lot because I've been to a lot here in California, but it is breathtaking out here. I've never seen so much salt in my life either, but the mountains are gorgeous. The sun's shining through the clouds. You got snow on the back of the mountains as well, but it is just gorgeous out here. Yeah. Unbelievable. On the Black Mountain side of Death Valley, there's a lot of tertiary volcanics and quaternary alluvium, just, rocks that have tumbled down off the mountains and deposited in alluvial fans and stuff. But the tertiary volcanics and some of the alluvium has beautiful colors that you can see in the rocks here. And whenever you see these like bright greens and reds, that's all due to iron.
The greens due to reduced iron, the reds due to oxidized iron. And it's all because of hydrothermal alteration from hydrothermal fluids flowing through the rocks after deposition. And any layers that are like tan either don't have iron in them, or it was leached out, or it just wasn't oxidized or reduced to cause this green or red color. Cool. There's actually a place in here we already visited, I'll put some B-roll in, called Artist Palette, that you can see these colors come out pretty much everywhere. And it's really, really cool. Say hi, guys. Cam.